Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Jakob Bernoulli's Ars Conjectandi, published posthumously in 1713, stands as a monumental work in the development of probability theory. Far from a mere collection of theorems and proofs, it represents a systematic attempt to formalize uncertainty and to provide a mathematical framework for reasoning under conditions of incomplete knowledge. Its influence resonates even today, shaping fields ranging from statistics and economics to actuarial science and artificial intelligence. Understanding the Ars Conjectandi requires appreciation of its historical context, its mathematical content, and its lasting impact. Bernoulli's work emerged from a confluence of factors during the late 17th and early 18th centuries. First, the rise of empirical science, spearheaded by figures like Isaac Newton and Robert Boyle, placed an increasing emphasis on observation and experimentation. The need to analyze and interpret data became paramount, but existing mathematical tools proved inadequate for dealing with the inherent uncertainties involved. Second, practical problems related to gambling, insurance, and annuities spurred the development of probabilistic reasoning. Mathematicians such as Girolamo Cardano, Pierre de Fermat, and Blaise Pascal had already made significant strides in understanding games of chance, but their work remained largely fragmented and unsystematic. Finally, the burgeoning field of statistics, then known as political arithmetic, sought to quantify social and economic phenomena, providing further impetus for a more rigorous treatment of probability. The Ars Conjectandi is divided into 4 parts. The first part provides a thorough commentary on Christian Huygens' treatise De Ratiocinae in Ludo ali Reasoning in Games of Chance, published in 1657. Bernoulli meticulously analyzes Huygens' propositions, offering alternative proofs, generalizations, and extensions. Importantly, this section established a firm foundation for subsequent developments, and it served as an accessible entry point for readers unfamiliar with the existing literature. Bernoulli goes beyond merely reiterating Huygens' results. He refines his arguments, introduces novel approaches, and foreshadows his own later contributions. The second part delves into the theory of combinations and permutations, fundamental tools for calculating probabilities. Bernoulli provides a comprehensive treatment of these topics, drawing on the work of previous mathematicians, but also introducing original methods and notations. His approach is characterized by a rigorous attention to detail and a commitment to providing clear and concise explanations. Here, Bernoulli essentially codified the combinatorial principles that are indispensable for calculating probabilities in scenarios involving discrete outcomes. He presents formulas for determining the number of ways to choose a subset of elements from a larger set, arrangements of objects, and partitions of a whole into parts. This section illustrates a meticulous care with which Bernoulli laid the groundwork for his subsequent probabilistic investigations. The third section directly addresses games of chance. Here Bernoulli applies combinatorial methods to derive probabilities associated with various games, encompassing dice games, card games, and lotteries. While this section provides valuable insights into the mathematics of gambling, its significance extends far beyond recreational pursuits. Bernoulli demonstrates how probabilistic reasoning can be applied to model and analyze situations involving uncertainty and risk. For example, he calculates the probability of winning a lottery, the expected payoff for a gamble, and the fair price for an insurance policy. The techniques developed in the section prefigure the tools employed today in actuarial science and financial modeling. The fourth part, and arguably the most important, presents Bernoulli's theorem, commonly known as the law of large numbers. This theorem provides a crucial link between theoretical probabilities and empirical observations. It states that as the number of independent trials increases, the relative frequency of an event converges to its theoretical probability. In other words, if we repeat an experiment many times, the observed proportion of successes will tend to approach the true probability of success. Bernoulli's formulation of the law of large numbers was far from straightforward. He grappled with the concept of convergence, it being challenging to express precisely what it means for a sequence of numbers to approach a limit. Moreover, he sought to quantify the rate of convergence, determining how many trials are needed to obtain a desired level of accuracy. His proof, while ingenious, involved intricate combinatorial arguments and lengthy calculations. To express the law of large numbers, let us assume an event with probability p of occurring. Let f be the observed frequency of the event in n independent trials. Bernoulli demonstrated that for any small positive numbers epsilon and c, the probability that the frequency f deviates from the true probability p by more than epsilon approaches 0 as n approaches infinity. Stated mathematically, for every epsilon greater than 0 and c greater than 0 there exists some integer n such that for all n greater than n, the probability of the absolute value of f minus p being greater than epsilon is less than c. This result, though expressed in somewhat cumbersome notation, represents a landmark achievement in the history of probability. The law of large numbers has profound implications for both theory and practice. It provides a theoretical justification for using empirical data to estimate probabilities. It underlies the statistical methods used in scientific experiments, opinion polls, and market research. It serves as a cornerstone of statistical inference, allowing us to draw conclusions about populations based on sample data. The Ars Conjectandi was not received without critique. Its complexity and rigor made it inaccessible to many contemporary readers. Some mathematicians questioned the validity of Bernoulli's proofs, particularly those related to the law of large numbers. Others felt that the focus on games of chance trivialized the subject matter and failed to appreciate its broader applications. However, over time, the Ars Conjectandi gained increasing recognition as a seminal work. Later mathematicians, such as Abraham de Moivre, Pierre-Simon Laplace and Simeon Denis Poisson, built upon Bernoulli's foundations, extending his results, simplifying his proofs, and applying his ideas to new domains. The law of large numbers, in particular, became a central focus of research, leading to more general and refined formulations. One notable extension of Bernoulli's work came from de Moivre, who derived the de Moivre-Laplace theorem, a precursor to the central limit theorem. The central limit theorem states that the sum of a large number of independent and identically distributed random variables, regardless of their original distribution, will be approximately normally distributed. This theorem provided a powerful tool for approximating probabilities, and it has become a cornerstone of statistical inference. Laplace, in his theory, Analytique des probabilités, analytical theory of probability of 1812, further generalized and applied Bernoulli's ideas, solidifying the foundations of classical probability theory. Laplace emphasized the importance of probability in understanding natural phenomena and in making rational decisions under uncertainty. He applied probabilistic methods to problems in astronomy, geodesy, and demography, demonstrating the versatility and power of the Poisson, in his Recherches sur la probabilité des jugements en matière criminelle et en matière civile, research on the probability of judgments in criminal and civil matters of 1837, explored the applications of probability to legal and social problems. He considered the probability of convicting an innocent person, the reliability of eyewitness testimony, and the fairness of jury verdicts. Poisson's work highlighted the potential of probability to inform public policy and to improve the administration of justice. The Ars Conjectandi also had a significant impact on the development of statistics. Adolphe Quetelet, a Belgian statistician, championed the use of statistical methods to study social phenomena. He collected vast amounts of data on crime, poverty, and education, using statistical analysis to identify patterns and trends. Quetelet's work helped to establish statistics as a legitimate scientific discipline, and it paved the way for the development of modern social science. Bernoulli's influence extends far beyond mathematics and statistics. His ideas have found applications in diverse fields, including economics, finance, engineering, and medicine. In economics, probability theory is used to model market behavior, to assess risk, and to make investment decisions. In finance, probabilistic models are used to price options, to manage portfolios, and to evaluate credit risk. In engineering, probability theory is used to design reliable systems, to optimize performance, and to assess safety. In medicine, statistical methods are used to analyze clinical trials, to diagnose diseases, and to predict patient outcomes. Even contemporary artificial intelligence research owes a debt to Bernoulli. Bayesian networks, a powerful tool for reasoning under uncertainty, are based on probabilistic principles that can be traced back to the Ars Conjectandi. These networks are used in a wide range of applications, including medical diagnosis, spam filtering, and machine translation. The enduring legacy of the Ars Conjectandi lies in its systematic approach to quantifying uncertainty and in its demonstration of the power of probabilistic reasoning. Bernoulli's work provided a foundation for subsequent developments in probability theory and statistics, and it continues to inspire researchers and practitioners today. Consider the modern application of clinical trials. The backbone of evidence-based medicine relies on statistical significance, p-values, and confidence intervals. These all stem from the framework Bernoulli helped establish. Without understanding probabilities, evaluating the effectiveness of medical treatments becomes impossible. Moreover, the Ars Conjectandi offers valuable lessons for decision-making in the face of uncertainty. In a world characterized by incomplete information and unpredictable events, the ability to assess probabilities and to weigh risks is essential. Bernoulli's work reminds us that rational decision-making requires a clear understanding of the limitations of our knowledge and a willingness to embrace uncertainty. The Ars Conjectandi represents far more than a historical artifact. It embodies a timeless quest to understand the nature of chance and to harness its power for the betterment of humanity. Its pages offer profound insights into the art of conjecture, which remain relevant today. It is the mathematics but the philosophy of confronting the unknown. Jakob, Bernoulli's masterpiece continues to challenge and inspire, inviting us to explore the vast and fascinating realm of probability.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.